Okay, so we're going to go ahead and take a look at another graphing example of a piecewise function. Okay, so if you didn't check out the last video, make sure that you do. That way you kind of had the fundamentals and you know some of the vocabulary that I'm talking about. But let's go ahead and take a look at this example. So as you can see here, we have our function f of x is equal to, and notice I have three subfunctions. I have three different rules, okay? What that means is, remember, I'm going to have three different pieces to the graph. That's what this means. Okay, since I have three different rules, I'm going to have three different pieces to the graph. And remember, our domain restrictions are going to tell us where we graph them, okay? So what this first piece here is saying, okay, remember f of x is y. So this is saying, hey, graph y equals, and then each of these individual pieces where we want to graph them. So this first piece here, okay, this first piece here is saying graph y equals 1/2 x plus 2 when x is less than -4. That's what that's saying, okay? Now remember another thing about the domain restrictions. It not only tells you where we want to graph them, but these numbers here also tell us the starting and stopping points. That tells us the starting and stopping points, okay? So last video, I just went ahead and made like a table for every single one. I'm not going to necessarily do that here, okay? What we're dealing with here is 3 lines, so we can just go ahead and use slope-intercept form to figure out each of these lines, okay? What I am going to figure out, though, is where the graphs start and stop, okay? So what I'm going to do is I'm going to first find out where this graph stops, because we're stopping when x is -4. So what I need to do is I need to plug in -4 to find out what that point would be. So I'm going to plug in -4. And you can do a table. Once again, I just want to show a different way of doing this. It might be a little bit quicker for those of us that are a little bit more advanced. So I'm plugging in -4 for x. And that's going to get us 1/2 times -4 is -2. -2 plus 2 is 0. I didn't actually mean for that to happen. That's kind of nice. So what this is saying is when x is -4, y is 0. Okay, so I'm going to go ahead and plot that point. But notice that's where this graph ends, and since it's not or equal to, it technically doesn't exist there. So I need to use an open circle. So I need to use an open circle at the point -4, 0, okay? So that point doesn't actually exist there. It's telling us, hey, we need to stop right at -4 for x. This is where we stop. And now from here, you can make a table to find the rest of your points, or you can use slope, okay? The slope of this particular graph is 1/2, so I'd be going up 1, right 2, up 1, right 2. However, this graph doesn't exist when x is greater than -4, so I'm going backwards. So if I would be going up 1, right 2, that means I'd actually be going down 1, left 2. Down 1, left 2. Down 1, left 2. And this is going to be this particular graph because we're only graphing this when x is less than -4, and x is less than -4 when x is like -6, -7, -10, and so on. So I'm going to connect that forever going in that direction. So that's the first piece of our graph. Okay? That's the first piece of our graph. Now the next part, this is saying graph y equals -x minus 4 when x is in between. This is what that's saying, okay? It's saying -4 is less than or equal to x, which is less than 1. That means x is in between -4 and 1, okay? Now, in the last video, we didn't have an example like this. We're having it start somewhere and end somewhere. So I'm going to want to make sure I get both of those points exact. So I'm going to go ahead and first plug in -4. So I'm going to plug in -4 for x. So -x, which is -4, minus 4. And we get y equals 4 minus 4. And we get y equals 0. So I need to go ahead and plot that. But, I already have that as an open circle. I already have that point. That was a point from the previous rule. Well, in some cases, these piecewise functions actually connect sometimes. It doesn't happen very often, but it does happen from time to time. And This was open in a particular rule, but it's actually closed in the next rule. So if you ever have a case where you have an open circle and a closed circle and they meet up, the close always overtakes the open, okay? Or equal to will always trump not or equal to, okay? So just like I normally would, since it was or equal to at -4, I use a closed circle, okay? Now I can use slope, I can figure that out, but I want to really quickly make sure I find out where we stop. This started when x was -4. It's going to stop when x is 1. So I'm going to want to go ahead and plug in 1. So I'm going to plug in 1 for x, so that's negative x minus 4, which is going to get me -1 minus 4, which is going to get me y is equal to -5. So when x is 1, y is -5. So I plot that point. But real quick, notice it's not or equal to. So I use an open circle. Remember, or equal to, closed circle, not or equal to, open circle, okay? And from here I can use slope. The slope of this particular graph is -1, so I'd be going down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. And then notice I get back to where I stopped. So I connect that particular segment. So notice since this one started and ended somewhere, it gave us a starting and ending point, that it's just going to be a line segment like so. Okay? Now, the last part. This is saying graph y equals 5 when x is greater than or equal to -1. Well, y is 5, y equals 5 is just a horizontal line. So if I plugged in 1 for x, y is just going to be 5. If I plugged in 2 for x, y is going to be 5. If I plugged in 3 for x, y is 5. Since there's no x to plug in, that's why y will always be 5. So that's just going to be a perfectly horizontal line. So when x is 1, y is 5. So I can go ahead and plot that point. And since it's or equal to, it's going to be closed. And then when x is 2, y is 5. When x is 3, y is 5. Notice that it's not changing because there isn't an x on that 5, okay? So this is going to be a perfectly horizontal line. Oops, this is going to be a perfectly horizontal line. And it's when x is greater than or equal to 1, which is all values to the right of 1. So that would be our graph, okay? So notice this was a 3 subfunction piecewise, and we have 1, 2, 3 different pieces to this graph, okay? And we also covered what happens when 2 subfunctions meet, okay? If one of them is or equal to, that's always going to overtake and make it closed, okay? There are some cases where both will not be or equal to, and it will just remain an open circle. It will remain undefined at that point. But in a lot of cases, you will have one of them where it's or equal to, okay? So that's just another example. I'm going to go ahead and do one more video of graphing piecewise functions, and we're going to get this one to be a little bit crazier and maybe introduce something that's not just a line, okay? So make sure that you check that out. Make sure we're practicing piecewise functions. Check out the next video.